very warm welcome to the course of Elements of Mechanical Engineering. In this lecture, we are going to study the introduction and classification of hydraulic turbines. My name is Atchuta Ramacharyulu and I am working as an assistant professor in the Department of Mechanical Engineering. We are in the second module where we are studying boilers and turbines. The first part is all about boilers and the second part is all about hydraulic turbines. So in this lecture, we are going to see the introduction of a hydraulic turbine and the different classification of hydraulic turbines. Now, let us see what is the basic definition of a hydraulic turbine. A hydraulic turbines are the prime movers that converts the energy of the falling water into a rotational mechanical energy and consequently to an electric energy through the use of a generator. Now, we know from our childhood, the basic understanding of the turbine is that it is placed in the flow of water where it will produce electricity. It is not that simple. When we are using a turbine, when we keep a turbine in the direction of flow of water, the water should be touching the buckets of the turbine. Buckets are nothing but the cups placed on this turbine. So it should be done in a most effective way. Otherwise, we cannot produce the electricity at our required rate because we are using sophisticated machines. Like we will use hydraulic turbines, generators which are connected with the help of shafts and all. So all these things has to work in union. They have to work combinedly and synchronously so that then we can produce electricity at our required rate. So every generator has a rated RPM where at that rated RPM only it can produce electricity. So our turbine, which is connected to the generator for producing mechanical energy, so this turbine has to rotate at the rated RPM of the generator. Only then the electricity can be produced. Now, in this picture, we can see a turbine, which is a Pelton wheel turbine. This is Pelton wheel. So George Pelton is the name of the scientist who first invented the turbine. This is an open atmospheric turbine where the pressure in this turbine or the pressure of the water is equal to the atmospheric pressure. This is all open. We can see the working. So sometimes in our laboratories for academic purpose, we will have small types of turbines where we can actually see the water flowing on the buckets and we can see the rotation of the turbine. And from there, we can understand how sophisticated a simple machine can be. So we can see in this picture, we have a wheel which is made up of aluminum. So the best thing for aluminum is it is lightweight and also it is stronger. Now this aluminum wheel, which is hydraulic turbine. So this turbine is placed on a shaft which is attached to a generator. Now we will have some ball bearings inside the shaft so that this hydraulic turbine wheel will move very freely. Now we have some nozzles here. So these three things are called nozzles. They will have some decreasing diameter. Decreasing diameter will make the water coming out of this nozzle to increase its pressure and velocity. So when the water flows through this nozzle, due to decrease in the cross-sectional area, the water coming out of the nozzle will flow more fastly. Its velocity will increase as well as the pressure. Now what happens is, we have to control the flow of water that is coming out of this nozzle. So nozzle is like just a pipe which is hollow inside. So inside this hollow nozzle, we will place a device called spear. Spear is nothing but it is a conical type metallic rod which is placed into the nozzle so that the flow of the water can be controlled with the help of this nozzle. So when the spear is moved to the right side, that is, it will be pushed into the hole, then the flow of water will be less. When it is moved back, that is, push it to the other side of the nozzle hole, then more water can go out of the nozzle. So this is how we can control the flow of water flowing through the nozzle. So whenever the water coming out of the nozzle, you can see in this picture, all the nozzles are placed in tangential direction to the rotation of the hydraulic turbine. See, this is the circular wheel, and we have turbines through which the water can flow in tangential direction to the rotation of the turbine. So all the things are placed in tangential direction itself. Everything is tangential. So whenever the water coming out of the nozzle will touches this bucket or vane. So this is called vane or bucket, because it is very cup shaped thing attached to the wheel. So this cup shaped thing, when the water touches on this cup, it will try to hold the water for a shorter period of time, which will make or create some force on the cup. Now there are series of cups placed on this turbine wheel, which will make the entire thing rotate. So everything is placed in the circular motion, and we are forcing the water to touch the plates in tangential direction. So this will make the turbine wheel rotate in clockwise or anti-clockwise direction, depending on the motion, depending on the arrangement of the nozzles. Now, the turbine wheel consists of a rows of blades that are fixed on the rotating shaft. So these are all fixed tightly. They are made as a single set of unit. Now, when the water is coming out of the nozzle, it will make the turbine rotate. Now this turbine, which is in connected with generator, also will rotate. So the shaft is same for this turbine and the generator. So whenever the turbine rotates, the generator also will rotate, and it will produce some electricity. Okay. So this is the basic definition of any hydraulic turbine. And the turbine you are seeing in this slide is Pelton wheel turbine, which is open atmospheric turbine, and it will have pressure that is equal to the atmospheric pressure. Why we are talking about the pressure? Because in other types of turbines, the pressures are more than the atmospheric pressure. That is why the pressure in this turbine is atmospheric. It is directly equal to atmospheric, and also the entire turbine structure is open to atmosphere. There is no closed cross section. At least we have a closed casing to control the flow or slashing of water. Whenever the turbine is rotating at high speed, the water will be splashing in all directions. To control that, we will have a casing. This casing will stop the water, and it will make the water to flow in only a single direction when this entire working of the turbine is done. So the water has to be controlled and collected at the bottom. Then it can be flowing into a canal or a water body. Okay, so this is hydraulic turbine. Now we'll see what are the different classifications of hydraulic turbines. So according to the type of energy at the inlet. So according to the type of energy, we have two types: impulse turbine and reaction turbine. So in impulse turbine, we have potential energy. In reaction turbine, we have both potential and kinetic energy. So we'll see in detail in the coming slides. And the second type is according to the direction of flow through the runner. So in this, we have tangential flow. Tangential flow is nothing but the flow of water is tangential to the rotation of the turbine wheel. And radial flow. Radial flow is nothing but along the rotation of the turbine wheel. And third one is axial flow. Axial flow is nothing but it is perpendicular to the rotation of the turbine. So this is perpendicular along the z-axis, like perpendicular to the screen. And then radial, axial, and mixed flow. Mixed flow is a combination of radial and axial flow of the water. Okay, these two are combined. We will get mixed flow of water which is entering into the turbine. And then third one is according to the head at the inlet of the turbine. So we have to understand the terminology of hydraulic turbines, where we will call the head. Head is nothing but the height of water present in the container or a turbine. Behind the dam, the height of water is called as head. So when we have this dam structure is like this. We have water here. So the height of water from the ground level is called as head, which is denoted with H. So this is a dam. Okay. So the height of water behind the dam is called the water head. It is called head. And why do we need to calculate the head? Because more the head, more the energy. So if the water is stored at a very high place, we can experience more potential energy. We know that potential energy is nothing but the energy possessed by some body by the virtue of its height. If more the height is there, more the potential energy will be there for the particular object. Now, so according to the head at the inlet, we have two types, that is high head and low head. And fourth one is according to the specific speed of the turbine. We have different speeds like low speed, medium speed and high speed. In the previous slide, we have discussed that the turbine has to rotate the generator with the mechanical energy that is supplied from the water. Now, when the turbine is rotating, the turbine has to make the generator to rotate at a rated RPM so that it can produce electricity. If the rated RPM is very less, the generator cannot produce electricity. It has to rotate at a particular speed. So based on this, we have three types of turbines like high speed, medium speed, low speed turbines, where depending on the type of generator, we can use different types of turbines. And then we're going to see the first kind, like impulse and reaction turbines. We'll try to understand what is an impulse turbine in this slide. So in impulse turbine, all the potential energy is converted into kinetic energy in the nozzle. So in impulse turbine, we have already discussed this. Like water is coming through the dam. A water dam is there. It is constructed across a river. Behind the dam, we have water stored at a height head, which we are calling as head. The height of the water is called head. And the water will be flown through a pipe. This pipe is called penstock. So a pipe is attached. We are not going to place the turbine in the flow of water. When dam gates are lifted, water will be flowing above the dam. We are not going to place the turbine at that place because the dam gates are not opened all the time, because we need electricity continuously. We have to place this entire thing in a separate structure. We cannot place this hydraulic turbine in the flow of water. We have to control the flow so that the potential energy of the water can be converted into mechanical energy, that is rotation of the turbine. Now, we will make the water to flow through the penstock. Penstock is a pipe which is of large diameter, like about 1 meter. So the water, when coming out of the penstock, it will make the turbine wheel rotate. So we have a hand wheel and spear arrangement here, and at the end of the pipe we have a nozzle, so we can increase the velocity and pressure of the water coming out of the nozzle. Now this water, when it touches the turbine wheels, it will rotate the turbine. Now when the turbine is rotating, the rotating shaft will rotate the generator so that we will produce electricity. Now in impulse turbine, what happens is the potential energy is converted into kinetic energy in the nozzle itself. So we will place the nozzle pipe at very height of the dam, from where it will produce, it will have a lot of potential energy because the water is stored at a very high altitude. The water will have high potential energy. This potential energy, when it is flowing through the nozzle, the water which is flowing through the nozzle, the potential energy will be converted into the kinetic energy because we have a decreasing diameter of the cross section where the water will come out at a very high velocity. So the potential energy is converted into kinetic energy in the nozzle. And the second point is the impulse provided by the jets is used to turn the turbine wheel. So whatever the speed of the water that is coming out of the nozzle, it will hit the turbine buckets. So the turbine buckets will experience a force on its surface. Whenever they experience some force in this direction from left to right, they will try to rotate because they are hinged at a central shaft placed on a roller bearing. So the pressure inside the turbine is atmospheric. So this is a open atmospheric turbine, which is nothing but the Pelton wheel turbine, which we have seen in the previous slide. So the pressure inside this entire turbine is equal to the atmospheric pressure, and this type is found suitable when the available potential energy is very high. So this kind of turbine arrangement or the impulse turbine arrangement is very suitable when we have water stored at a very high head. When the water is stored at a very large dam, that is, the height of the water in the dam is very high, then we can go for this Pelton wheel turbine, where we will have more potential energy. Then what happens if the water head is very low? Then we will go in selection for other types of turbines like reaction turbines, where the working of this reaction turbine is entirely different. It is placed in a closed chamber where the water will be flowing in a radial direction so that it will produce more electricity more efficiently. Because we have a closed chamber, we cannot lose any pressure of the water because the entire structure is closed. Every water droplet will try to create some force on the wheel of the turbine. So that is when we create energy more efficiently. So when we have more head, we will go for this simple construction, that is Pelton wheel. When we have less head, then we will go for other options. Now, the flow available is comparatively low. So this impulse turbine is very suitable when the flow is very low when compared to other types of the turbines like reaction turbine. In reaction turbine, we need more water flow. Here, we don't need more water flow when compared to reaction turbine, but we need more height, more head of the water. Okay, so this is the impulse turbine. The best example for impulse turbine is nothing but the Pelton wheel turbine, where we have seen the working of the Pelton wheel also. And second type of turbine, reaction turbine. So in reaction turbine, the available potential energy is progressively converted in the turbine rotor, and the reaction of the accelerating water causes the turning of the wheel. So here, the energy possessed by the water that will be converted into another form, like potential energy of the water can be converted into kinetic energy inside the runner or inside the turbine. Previously, we have seen the potential energy being converted into kinetic energy inside the nozzle itself, because the water, when it is coming out of the nozzle, it will have some kinetic energy, which means the potential energy is converted into kinetic energy. This entire thing happened in the nozzle itself. Now, in reaction turbine, this conversion of energy will take place inside the runner. So, what is a runner? The turbine wheel is called as runner. This entire arrangement is called runner. So, the entire thing is called runner, and the outside part, this is called casing. And we will have water coming out from the penstock here. This water will enter into the turbine in this direction, in this radial direction. Okay. Now, when the turbine, when it is rotating, the water will enter in this red color arrows are there. In this direction, the water will enter into the turbine, and from there, it will make the turbine wheel rotate. So, we'll try to understand the working in detail in the coming slides, where we will study the reaction turbines. The example for reaction turbine is a Francis turbine. So, as of now, we'll try to understand what is a reaction turbine. So, in a reaction turbine, the potential energy is converted into kinetic energy inside the runner. This process done inside the runner. So, there are many types of reaction turbines are there. They are radial flow, mixed flow, and axial flow machines. So, first thing is radial flow. That means in this diagram we can see this is a radial flow. The water is flowing around in radial direction. And second one is mixed flow, where the water will enter in this direction and it will come out in the perpendicular direction. So, from the center of the impeller or center of the runner, the water will come in the perpendicular direction. Okay. And then third one is axial flow machine. Axial flow machine is nothing but it will completely work. The water flow will in the axial direction only. Okay. Now see, radial flow machines are found suitable for moderate levels of potentials and a medium quantity of flow. And then the axial machines are suitable for low levels of potential energy and large flow rates. So depending on the type of requirement and the particular condition, we will select a different type of turbine. So this is reaction turbine, the second type. So the impulse and reaction turbines are the turbines based on the energy available at the inlet. In impulse turbine, we have the potential energy which is converted into kinetic energy itself in the nozzle. Whereas in reaction turbine, the potential energy will be converted into kinetic energy or mechanical energy inside the runner. So there is no nozzle here. Now let us try to understand the basic terminology of the turbines, definitions and heads. So we'll see what are the different heads available in the turbine. So we should know this terminology in order to understand the basic features of any hydraulic turbine. Now we'll see the first one is gross head. Gross head. So let us try to read the gross head definition. So the gross head is the difference between the water level in the reservoir and the water level at the tail race. So in the diagram we can see here we have a head race. Head race is nothing but the level of water behind the dam. So this is a dam structure behind which we have water. The level of water is up to here. Okay. Now, when the water is coming through this penstock, it will touch the turbine and it will fall here. After touching the turbine wheel, it has to be collected at some place. So, the level of water in the tail race is this one. Now, the difference between these two, the difference between these or the height between the water level in the tail race and the water level in the head race that is behind the dam, this height is called as gross head. It is denoted by H suffix G. So this is the first head we have to study, and net or effective head, the second one. The head available at the inlet of the turbine is known as net or effective head. It is denoted by capital H and is given by this formula. Now we'll see what is capital H. Capital H is nothing but it is the height between the head race and the water touching the turbine, the level of water touching the turbine. That means at this line. Okay, when the water is touching the turbine, it will be at a lower level when compared to head race. So this height is called H. It is denoted here, this height. This is called H. Okay, the height between, I'll redraw this. The height between the head race and the water level in the nozzle, it is called H. It is called as net effective head, and it can be calculated with this formula where H is equal to Hg, which is gross head, minus Hf. Hf is nothing but head loss due to friction, and H is nothing but head. Okay, we'll try to understand all these things in the coming slides. So, net or effective head is the head between the water level touching the turbine and the water level present behind the dam, that is head race. And next thing is, we have a formula here for Hf. So, Hf is nothing but head loss due to friction. Now, we'll try to understand what is head loss due to friction, why it is calculated or why it is taken into consideration while doing the calculations for the design of a turbine or a penstock. Now we know that water, when it is flowing through a penstock, the penstock is a pipe. The pipe will have some friction when the water is flowing through it. So we have to consider the friction of the pipe when the water is flowing through the penstock. Okay, now that is given by Hf is equal to 4FLV square. Here, F is nothing but the friction constant, L is nothing but the length of the pipe, V is nothing but the velocity of the water that is flowing through the pipe, and capital D is nothing but the diameter, and 2 into 2 times the gravity. So the gravity is also taken into consideration. So 4FLV square divided by capital D into 2 times the gravity. So F is the friction coefficient, L is the length of the penstock, V is the velocity of the water flowing through the penstock, D is the diameter of the penstock, and G stands for gravity, which is obviously 9.81 meters per second square. So this is the formula for head lost due to friction in the penstock. Now this head loss is shown here, Hf. Hf is the difference between the head that is lost when the water is flowing through the pipe. So it is a calculated value, but it is shown in this figure for understanding purpose because the sum of this H and Hf plus small h will gives you Hg. Okay, Hg, which is gross head, is equal to Hf plus capital H plus small h. Okay, so this will give you the gross head value. So okay, Hf is the head loss due to friction, and its formula is 4FLV square by d into 2 times the gravity. Now we'll see what are the different efficiencies. Okay, so in this slide we can see the efficiency is there are different types of efficiencies which has to be studied when we are trying to understand a turbine. It will have some efficiency, because why efficiency is very important when we are working with turbines. Because when we are using a turbine, the turbine has to use the potential energy or kinetic energy that is supplied from the water. When the water it is touching the turbine blades or vanes, the turbine has to rotate. When the turbine is rotating, it will have some losses, because the entire turbine is a mechanical structure. It will have some losses like frictional losses or movement losses. Okay, so the energy, the kinetic energy present at the nozzle, it may not be completely converted into mechanical energy due to some losses present. Just now we have seen there is a loss of friction, head loss due to friction. In this slide we have seen. Because of this, we have to calculate the efficiency. How much efficiently the turbine is working or producing electricity. So, among these different types of efficiencies, the first one is hydraulic efficiency. So, the efficiency will be represented with this symbol. It is called eta. Eta, which is like n, small n, extended. So, here we are studying hydraulic efficiency. So, eta suffix h. Now, the definition for the hydraulic efficiency is power developed by the runner to the power supplied at the inlet of the turbine. So, it is defined as the ratio of power developed by the runner to the power supplied by the jet at the entrance of the turbine. See here, it is the ratio. Power developed by the runner. Power developed by the runner, which is nothing but when the water is touching the turbine wheel will rotate and it will produce some mechanical energy. Why do this energy is calculated? Because this mechanical energy, with the help of a shaft, the turbine is connected to the generator. So along with the turbine, we have to rotate the generator also, because for the running of the generator, we need some energy. So power developed at the runner, which is due to the movement of the hydraulic turbine, that is taken as known numerator, and then power supplied at the inlet of the turbine. So whatever the power that is supplied, like potential energy, kinetic energy, or combination of two, this kind of energy will be supplied to the turbine at the inlet. So that value is taken in the, so this is power supplied at the inlet, this is taken in the denominator. So this ratio will give you the hydraulic efficiency. So simple way to understand the hydraulic efficiency is power inside the runner, power outside the runner. This ratio is nothing but the hydraulic efficiency. Now let us try to see a formula for these values. So here we have the power developed in the runner. The values are, this is rho, QA, VW1, VW2. So these are all the values of the water that is flowing through the runner or the inlet of the runner, that is like in the nozzle. So we have to calculate all these values. First one is rho. Rho stands for the density of water. QA is nothing but the discharge of the water that is coming out of the nozzle. And VW1 is the whirl velocity. WHIRL. Whirl velocity. Whirl velocity at the inlet, and VW2 is the whirl velocity at the outlet. We will try to understand all these things in the coming slides. As of now, we will see the formula for efficiency. And U, small u stands for velocity of the water. Velocity of the water. And small w is the weight of the water, q is the discharge of the water, and h is the head of the water. So when we use this formula, so the numerator is nothing but the power developed inside the runner, the denominator is the power supplied at the turbine. Now we have simplified this formula, and finally we get VW1 plus or minus VW2. Why do we have plus or minus here? So depending on the turbine, we will change the sign as it is positive or negative. So VW1 plus VW2 multiplied by the velocity of the water, G into H. G stands for gravity and H stands for head of the water. And finally, we will get HR divided by H. So here, we can see the simple formula for the hydraulic efficiency or hydraulic losses is delta H is equal to H minus. H stands for head and HR stands for velocity or the head lost due to the motion. Somehow we will lose some energy while the water is flowing through the turbine. So that is delta H is equal to H minus HR. HR stands for energy lost, or the head lost due to rotation in the water. And then the second type of efficiency. So we have seen the hydraulic efficiency. Now this is mechanical efficiency, which is denoted with eta m. Now it is defined as the ratio of the power obtained from the shaft of the turbine to the power developed by the runner. Okay, these two power differs by the amount of mechanical losses, bearing friction, etc. So this formula can be simply written as the ratio of shaft power to the bucket power. Now we have seen in the previous efficiency, that is hydraulic efficiency, we have calculated or we have tried to understand the relation between the energy available at the inlet and the energy inside the runner. Now in this formula, we will calculate the mechanical efficiency where we are going to compare the energy available at the shaft to the energy available at the bucket, that is runner. So when the runner is rotating, at the center we will have a shaft which is attached to the runner and it will rotate along with the runner. So when the energy available at this point, that is the energy of the bucket, and energy available at this point is energy available at the shaft. Now we will take this ratio and we will try to calculate the mechanical efficiency. How efficiently the energy is converted into rotation. Okay, the rotation of the turbine is converted into mechanical energy. Now there is a formula for this, and the shaft power is nothing but capital P, which is denoted with capital P, and we will have the bucket power, that is the power available at the turbine. Small w, QA, small w stands for weight of the water, QA is the discharge, VW1 is the whirl velocity at inlet and whirl velocity at outlet, divided by gravity multiplied by velocity of the water. Now finally we will get this formula. Capital P, which is the power available at the shaft, small w is the weight of the water, Q discharge, HR is the head loss. Okay, head loss due to rotation. Now for this example or for this definition, we'll try to understand what is the average value of the efficiency. Now the values of mechanical efficiency for a Pelton wheel usually lies between 97 to 99%, depending on the size and the capacity of the unit. See here, we will have a value between 97 and 99. So 97% of the energy available at the bucket is converting into shaft power. Okay. What about the remaining 3%? Like I will take 97%. The remaining 3% of energy will be lost due to friction, bearing friction, or mechanical losses. So somehow we have to lose something to gain a lot. So we'll see the next type of efficiency. This is volumetric efficiency. So here the definition for this is the volumetric efficiency is the ratio of the volume of water actually striking the runner to the volume of water supplied by the jet to the turbine. So this can be given in this formula, QA divided by Q. It is the ratio of volume striking the runner divided by volume that is coming out of the jet. So we will have a jet from which we will have water coming out, where we will place a turbine. So the amount of water here is nothing but Q, and the amount of water touching the turbine is QA. So Q is the water coming out of the jet and QA is the water that is actually striking the buckets of the turbine. So this ratio is taken as volumetric efficiency. How much volume of water is being utilized efficiently? So this ratio can be called as volumetric efficiency. And again, here the average values of this volumetric efficiency lies between 0.97 to 0.99. Okay. And overall efficiency. Overall efficiency will let you understand how efficiently the entire turbine is working, starting from the water coming out of the nozzle to the generator power. Okay. Now we'll try to understand the overall efficiency. It is defined as the ratio of power available at the turbine shaft to the power supplied by the water jet. Okay. So we'll take the power from the whatever the power that is available at the nozzle will be taken at the denominator, and in numerator will take the power that is available at the shaft. Okay. Simply this can be written as shaft power divided by water power. Shaft power, water power. So shaft power will be defined with capital P, and water power is denoted with small w QH. Okay. So the overall efficiency values of this volumetric efficiency lies between 0.85 to 0.90. That means it will stay between 85 to 90%. So we are losing around 15 to 10%. 10 to 15% of energy is lost while the working of the turbine, because most of the energy that may be lost in the pipe due to friction or in the bearing friction, mechanical losses, lot of things are there, because we have many moving mechanical elements. They will conserve some kind of energy, so that we will get the maximum efficiency is 90%. Okay. Now we have efficiencies of hydraulic turbine. We have a relation. We have a common relation between all the types of efficiencies, that is hydraulic efficiency, mechanical efficiency, and volumetric efficiency. When we multiply all these things, we will get overall efficiency. Simply, this has written in this formula: H, head loss due to rotation, divided by head, and P is the power of the shaft, W is the power of the water, and Q is the volume of water present at the turbine blade, and Q is the water available at the nozzle. So finally, multiplying all these values, we will get P into WQH. P over WQH, which is the same formula of the overall efficiency. So this is the relation. If you want to relate all these things, or if you want to calculate the other values, if we know some of these values of efficiencies, then we can use this formula. Overall efficiency is equal to hydraulic efficiency multiplied by mechanical multiplied by volumetric efficiencies. Okay. Now, if eta G is the efficiency of a generator, then the power output of hydro unit can also be calculated by using this formula. So far we were discussing about the water power and the turbine power or the shaft power. We are not studying about the generator. Okay. We will study only up to the shaft. Now, we have a formula which will calculate the generator efficiency also taken into consideration, so that we will consider the entire machine for producing electricity. So here the power output of the hydro unit, turbine plus hydro generators, this can be given by WQH, which is the water power, multiplied by overall efficiency and multiplied by the generator efficiency. So the product eta naught and eta G is also known as hydroelectric plant efficiency. So eta naught or eta overall is equal to, this is the efficiency of the turbine only. That is starting from the water that is coming out of the nozzle to the shaft power that is being generated. And after the shaft, when the shaft is connected to the turbine, now we'll come to the generator. The generator will have a separate efficiency. Generator is a rotating machine which will have separate efficiency. It is denoted with eta G. Now the product of these two, eta overall and eta generator, will give you the efficiency of the entire power plant. The efficiency of the thermal power plant, hydroelectric power plant. Okay. So this will give you the hydroelectric power plant efficiency. So in this lecture, we have seen the basic introduction of turbine, classifications of different turbines, and we have seen them some definitions like heads, efficiencies. That's all for today, and we'll meet in the next lecture. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.